Okay, so what did we do in the last lecture? Our goal is still to define the denotational semantics of Haskell, and we will do it today. And what is the denotational semantics? So what's the overall goal? Well, the overall goal is to define a function that takes Haskell expressions and maps them to some mathematical object. So we want some function, we will call it val for value, and this val function takes an expression, Haskell expression, and maps it to some mathematical object, and the set of mathematical objects that we regard is called DOM, and this contains objects for all kinds of Haskell expressions plus a little bit more. So how was DOM defined? Well, DOM contains a lot of things. Somehow this pointing thing is not there anymore. Here. So what does this contain? So this DOM is the smallest domain satisfying this equation. So it contains functions, so all the functions from DOM to DOM. It contains tuples, so it contains the empty tuple plus bottom, and it contains tuples with 2 components, tuples with 3 components, and so on. And it also contains the objects that we need for all other types, in particular user-defined types. So constructions N, those should be the objects that we need for objects that are built with a constructor of arity N. So if we have a constructor of arity N, then this is mapped to a tuple where the first component is the name of the data constructor and the remaining components are the arguments of the data constructor. And of course, sometimes we don't write it as tuples, but we write it as terms because then it looks more readable. And well, now it turns out that if we really want to define this mapping, then of course there could be free variables in an expression. So typically, an expression, somehow it's not possible to switch on the light here. No, that's not good. Okay, but the front light, now even the front light works, okay. But in general, such an expression could contain free variables. So an expression could contain free variables. For example, if we have an expression like this, plus xy, then the question is, what does that mean? What does plus mean? What does x mean? What does y mean? And so, in general, it only makes sense to define the semantics of an expression if we know what the free variables stand for. And therefore, we do not just say that we want to know the value of this expression, but we want to know the value of this expression in a certain environment. And the environment tells us what all these free variables mean. So we want to know what is the meaning of this in an environment. So this comes from an environment, and this thing comes from the set of expressions. So that means this value function takes an expression, and it takes an environment, and it gives you back an element of DOM. So what is an environment? An environment is just a mapping from variables to elements of the domain. And it should only be defined on finitely many variables. I mean, these are the variables that were defined in your program. And all these other variables that you might have, they are undefined. We sometimes write this. So we write that the environment looks like this. Variable 1 is instantiated with the domain element d1, and variable n is instantiated with the domain element dn. And sometimes it is necessary to modify environments because, well, we have already defined some variables, but some other variables are still undefined. To express this, we use the addition operation. And this means this is the environment row 2, but updated by the new environment row 1. And this is defined as follows. This new environment should do the same thing as row 2 whenever row 2 is defined. And only if row 2 is undefined, then it should behave like row 1. And so the idea is we start with an initial environment, which we denote by small omega. And this initial environment defines the semantics for all predefined operations in Haskell. So for example, for addition, the plus symbol, or map, or filter, all the things that are predefined in Haskell, of course, we need to know their semantics. And this should be done by this initial environment. And then afterwards, the program of the user adds additional definitions. And these additional definitions, they extend this environment. So then we use this plus operation and extend the initial environment by new definitions for the user-defined functions. So that's the idea. And we will always require that if we want to compute the value of an expression in an environment, that this environment is defined for all free variables that occur in here. So the environment row must be defined for all free variables occurring in the expression. Now, what does free variables mean? Well, a variable is free if it is not bound by a lambda and not bound by a let. Let's define this properly. So what are the free variables of a Haskell expression? So for which variables in the expression do we need to know the semantics on beforehand? So we take a Haskell expression and just define what are the variables in there that we consider to be free. So for a simple Haskell expression, expression exp, its free variables, and the set of free variables is denoted as free of exp, are defined as follows. And well, to make life simple, we define the whole semantics first only for a subset of Haskell, namely for simple Haskell. And so here we only look at simple Haskell expressions. What is simple Haskell? We defined that in the last lecture. Well, it's just a subset of Haskell where we omit some complicated things, and in particular, we omit everything connected to pattern matching. So what is a simple Haskell program? It's a program without type synonyms, so you don't have the keyword type. I mean, that's just an abbreviation, like string is an abbreviation for a list of characters. There are no type classes and no predefined lists. So if you want to use lists, you have to define them yourself. There's a hard restriction, namely the program consists of just one single defining equation of this form. A variable on the left-hand side and an expression on the right-hand side. And the expression is built according to this grammar. So it can be a variable, it can be a data constructor, an integer, a floating point number, or character. It may not be a predefined list, but it may be a tuple. It may be an application where you apply one expression to the next. It may be an if-then-else expression. It may be a let expression, so we have let, but not where. And it may be a lambda expression, but only a lambda expression with one single argument. And this may not be a pattern, but must be a variable. So since we only have one single equation, and since we don't have the case construct, there is no pattern matching anymore. So this makes life a bit simpler, and how to extend this to pattern matching, we will see afterwards. So for all these expressions, we now define what are the free variables in such an expression. So let's go through all the cases. So if we have a variable, what is the set of free variables in there? Well, it's just this variable. So this is the only variable occurring in this expression, and it is free. I mean, there's no lambda there, no let there, which could bound this variable, so it is free. What happens if we have a data constructor or an integer or a floating point or a character? So if we have an integer or a floating point number or a character. Well, there is no variable here, so there are no free variables. So this has no free variables. What's the next thing? If we have a tuple, how do we get the free variables in here? So a tuple of the form x1 to xn. Well, if we want to compute the free variables here, we just take the free variables from x1 and the free variables from x2 and the free variables, well, from all these components and unite them. So this is the union of the free variables of x1 and the free variables of x2 and finally the free variables of xn. What's the next thing? The next thing is application. So what are the free variables of the expression where we apply x1 to x2? Well, that's also simple. We just take the free variables from both of these sub-expressions. So the free variables of x1 united with the free variables of x2. Also, if then else is the same thing. We just unite all the free variables in the sub-expressions x1, x2, and x3. So if we have if x1, then x2, else x3. The free variables here are just the union, it's just the union of the free variables in the sub-expressions. x2 and the free variables from x3. Now the only interesting cases are the last two cases. So a let expression. What are the free variables in the expression let var equals exp in x prime? This should read so. There's a prime missing. Now of course this exp here and this exp, they don't have to be the same. So let var equals exp in x prime. Well, what are the free variables? Now this variable is not free because how we call this variable, that doesn't really matter. I mean, if we write let x be whatever plus 2y in plus xz, whether we write this or whether we write let x prime be plus 2 and y in plus x prime z, that shouldn't really make a difference. I mean, in both cases, this variable x stands for the term plus 2y. So whether we write this or this, well, it doesn't matter how we call this variable x here, because x is bound. So x is a bound variable, and the names of bound variables are completely arbitrary. So the free variables in here, what should they be? Well, x should not be free, but y is free. So we need to know what y means in order to compute the meaning of this expression, and z is free as well. So the free variables here are y and z. And this means that if we want to find out the semantics of this let expression, we need to know the value of y and we need to know the value of z. We don't need to know the value of x. I mean, if x had a value before, it doesn't matter anyway because this x is overwritten here. And we don't need to know the value of any other variable because no other variable occurs here. Well, depending on whether plus is a variable or not. So maybe plus is also a variable. So then it should be plus as well. And here it should be the same. So these are the free variables of this expression. So in general, the idea is for a let expression, we take the free variables in x and in x prime, but var should not be free. So we take the free variables from x and the free variables from x prime. But from this set, we omit the variable var. And, well, a similar definition is used for lambda expressions. So what are the free variables of this expression? Lambda var goes to exp. All the variables except var. Because whether I write lambda x goes to x plus 2, or whether I write lambda y goes to y plus 2, that doesn't really matter. In both cases, it's the function that increases its argument by 2. So the free variables of this are the free variables from exp, but not var. So this is the definition of free variables. And now with this, we can start defining the semantics. So now we can finally define what it means, what the semantics of an expression is in a certain environment. And the requirement is that all free variables in this expression, they must be, for them we need to know what their semantics is by looking into the environment. So where rho is defined for all free variables of exp. So for all variables in free of exp. So let's do this step by step. We only have to regard those cases that you can see on the slide there because we just look at simple Haskell expressions. So how do we do this? Let's start with the case where the expression is just a variable. So what is the value of this expression, which is just a variable, in a certain environment? How do we define this? Well, we just have to look into the environment. This is just a simple variable, and we have required that the environment has to be defined for all free variables occurring here. So the environment has to be defined for this variable, and it will tell us what this variable means. So we define the value of such a variable to be whatever the environment tells us. So for example, if I want to know, I have some variable x occurring in my expression, and I want to know what does this mean. Well, I don't know. It depends on the environment. And the environment might say that x has been set to the number 2, for example. So this will be, for example, it could be 2. If I'm in an environment where I have the declaration x equals 2 before, then this will be the definition. This will be the definition of x. Or, for example, if I want to know what is the semantics of map in the initial environment. Now, map is a predefined function symbol, and therefore the initial environment knows what it does. It will be whatever the initial environment tells me about map. And, well, this is the function that maps another function to all elements from a list. So it's the map function. And you know what that means. Okay, so this is the value of variables. Now what's the next kind of expression? The next kind of expressions are data constructors. Let's first look at data constructors of arity 0. So let's look at the value of a data constructor of this form, const to 0, and this const to 0, this should be from con0 bottom. So con0 is the set of all data constructors of arity 0. So it will contain things like true and false, and also all the integer numbers like 0, 1, 2, 3, -1, -2, -3, all the characters, all the floating point numbers. They are all data constructors of arity 0. And we want to know what is the meaning of these data constructors. Well, let's look at so the result of this should be some element from DOM. What was DOM? DOM was this large set containing all the mathematical objects that we need. So in particular, it contains constructions 0. So constructions 0, these are elements from con 0 bottom. So it contains, things that start with a constructor of arity 0, they will be mapped to elements from construction 0. And terms that start with a constructor of arity 1 will be mapped to objects from this set, constructions 1, and so on. So this will be mapped just to itself. So this will be constr 0. And, well, this DOM is a large coalesced sum. And if we look at this in a very precise way, then these elements are marked by the set where they come from. So this is marked by saying, well, this comes from the subset constructions 0. So this means this is marked as coming from the subset constructions 0. And this in turn is marked as coming from the set DOM. So this in means it is marked in an appropriate way to make clear from which subset this thing is coming. So this was, if you look at the definition of coalesced sum, then we said that every element has to be marked by the original set that it comes from. And in order to avoid writing down this marking, we sometimes write these in statements behind it. And this makes clear that this comes from this subset, and it in turn comes from this set. So for example, but in the examples I will omit this in thing. So let's look at some concrete constructor of arity 0, for example, the number 5. So if I want to know what is the meaning of this thing here, well, the meaning of this thing is the number 5 in construction 0 in DOM. So nothing spectacular yet. Now what happens if we have constructors of larger arities? So what's the meaning of a constructor that has not arity 0, but arity, a larger arity? So what's the value of a constructor, a data constructor of arity n in some environment rho? Now if n is greater than 0, so n is greater than 0, then what we expect is that this is the meaning of this is a kind of function. So it should be some function from the domain which waits for n arguments. And if it gets n arguments, then it produces the corresponding object from the domain. So it's a function f where, well, f is a function that produces constructor ground terms, so terms built with this data constructor. So where f is a function, f is a function which takes n arguments. So n arguments d1 to dn from the domain. And if it gets these arguments, well, then it returns the corresponding object from constructions n. And how does this object look like? It starts with the name of this data constructor. So it starts with the name constructor n. And then we have d1 to dn. So in other words, f looks as follows. f is a function in functions in DOM. And how does f operate? So f takes n arguments from the domain. And what does f return? Well, it returns this new object, constr n, comma d1 to dn, in constructions n in DOM. In constructions n in DOM. So this was the second case. So let's maybe put this on the slide in parallel. So here comes the large definition of the semantics of Haskell programs. So we have now defined these first three cases where we regard the semantics of variables and the semantics of both data constructors of arity 0 and data constructors of higher arity. So let's look at an example for this. So let's take a data structure where we have a data constructor of arity greater than 0 and then see what comes out. So let's maybe take our data structure for natural numbers. Here's the example. So suppose I have this data structure for natural numbers. So nuts, which has the data constructors 0 and suck. And the arity of the successor constructor is 1. And now I want to know what is the value of this expression, suck. Well, according to the definition, it's a function. It's a function f. And what does this f do? Well, this f waits for an argument. So as soon as I give an argument to f, then what will be the result? The result will be the object that corresponds to the term that starts with suck, and the argument has the value d. So the result will be suck, comma d in constructions 1 in DOM. So now you can see what happens if we have partial application. No, okay, that we will see later. But you can see that constructors of arity greater than 0 are now, the semantics of them is a function which waits for arguments, and if the arguments are there, they return the corresponding constructor ground term. I mean, you can also denote this as suck applied to d. Sometimes we use the notation as terms, and sometimes we use the notation as tuples. So this is the semantics of data constructors. Now what's the next thing? The next thing are tuples. What is the semantics of a tuple? So suppose I have a tuple with x1 to xn. And I want to find out the semantics of this. Well, in the domain, we have also tuples. So the semantics of this expression will be the tuple consisting of the semantics of x1, the semantics of x2, and so on, and the semantics of xn. So this is the tuple where consisting of the semantics of the first sub-expression, so the semantics of x1 and the semantics of x2, and then finally the semantics of xn. So this means now we define what all the language constructs mean. And we have defined that, well, constructors mean themselves, but if it's a constructor of higher arity, then it means a function. And now we define that these round brackets mean tuples. So I'll also put this on the slide over here. And one should note that this is only defined for tuples of arity 0 and arity greater or equal than 2. So if I write something like this and I have either 0 components or at least 2 components, then this is defined to be the tuple of these values in the subdomain tuples n in DOM. Tuples n is the subdomain for tuples with n components. We don't do this for tuples with just one single component. And why? Because the semantics of tuples with one component in Haskell is the same as the component itself. I mean, this is how the semantics of the language is defined. So as soon as we have just one single component in the tuple, we have a slightly different definition. So if we have just one single component here, something like this, with round brackets around it, then these round brackets play no role. So the semantics of this thing is the same as the semantics of the expression without brackets. So the definition above is only valid if n is 0 or n is greater or equal to 2. Now the next case are applications. So what happens if we apply one expression to another expression? So what is the semantics of something like this, where one expression is applied to another expression? So now we have to define formally what it means to write two expressions beside each other in some environment rho. Well, what does that mean? Intuitively, we know what that means. It means that this here should denote a function. So the semantics of expression 1 should be a function, and the semantics of the whole thing should result from applying the semantics of x1, namely the function that corresponds to x1, to the semantics of x2. So it should be something like this. The semantics of x1 should be some function. So the semantics of x1 in this environment rho should be some function f in functions in DOM. If this is not the case, then something went wrong and this is not a well-typed expression. And if we know that, if we know the semantics of x1, which is this function f, how can we get the semantics of this whole thing? Well, we have to apply the semantics of x1, so we have to apply f to the semantics of x2. So f is applied to the semantics of x2. So let's try it out and see whether this looks plausible. So let's look at an expression where one expression is applied to another one. So for example, the expression suck 0. So to find out what the semantics of this composed expression is, we first have to find out the semantics of suck. Now the semantics of suck, I already wrote this down on the blackboard above. The semantics of suck is this function f. It's this function f above which waits for an argument and then it returns the tuple suck, comma, the argument. So the semantics of suck is the function f above. And so the semantics of the whole thing is f applied to the semantics of 0. So it's f applied to the semantics of 0. And what is the semantics of 0? Well, 0 is a constructor of arity 0, so the semantics of 0 is just 0 itself. So the semantics of 0 is 0. And therefore, what is the result here? So it's f applied to 0. And f applied to 0 is, if you look at the blackboard above, it is the tuple consisting of suc and this argument. So it's the tuple consisting of suc 0. And so by this definition, we have now made clear that writing two expressions beside each other means that the semantics of the first expression, which is a function, is applied to the semantics of the second expression. And I also wrote this on the slide. So these are the semantics of these first kinds of expressions. Now what's the next possibility? The next possibility is if then else. So we now formally define what if then else means. Of course, intuitively you know what if then else means, but we can really define this formally. So what is the semantics of an expression of the form if x1 then x2 else x3? Well, there are two possibilities. Either it's the semantics of x2 or the semantics of x3. So the result is it's the semantics of x2. And when is this the case? Well, to find out whether it's the semantics of this, we have to look at the semantics of that, of the condition. If the semantics of this is true, so if the semantics of x1 is true, and here true comes from construction 0 in DOM, in constructions 0 in DOM, then the result should be the semantics of x2. And if the semantics of x1 is false, then the result of the whole expression should be the semantics of x3. So if this has the semantics false, and well, this should be an expression of type bool. So this will be mapped to an element of the domain which corresponds to Boolean expressions. And well, there are just three possibilities. It could be true, it could be false, or it could be bottom. So this case has to be considered as well. So if the value of this is bottom, then what should be the value of this if then else expression? Well, it should also be bottom. So these are the three possibilities. And well, to continue, I brought a second slide where we have the definition of the semantics for the remaining expressions. And this is all rather straightforward except for let expressions. So let expressions are the only case where something interesting happens. And the reason is that in a let expression we may have recursion. Yes?
Which bottom is that? Is there only one?
There's only one bottom because this domain was built as the coalesced sum of many subdomains. And whenever we build the coalesced sum, so this thing, all the bottom elements are identified. And so there is one big bottom element which is on the very bottom of the whole domain. So this is the at most undefined element you can think of. Okay, so let's define the semantics of let expressions, but before we do that, I will wipe the board. Okay, so now the next goal is we want to define what is the value of an expression of the form let var equal exp in x prime. And the main problem here is that this could be a recursive definition. So let's first regard the case where this is not a recursive definition, and let's see how we would do it there. So first, regard a non-recursive declaration so I mean that this variable should not occur in exp. So var does not occur in the free variables of exp. Then what should be the semantics of this? Well, essentially the semantics of this is this expression. It's x prime. But the environment has been modified. The new environment is not just rho, but moreover, we know that this variable now has the value exp. So the idea is the value of this thing, let var equals exp in x prime. This should be the semantics of x prime. But not in rho, but in some new environment rho prime. And this results from rho by extending it by this new definition, because now the variable var has the meaning exp. By extending it due to the declaration var equals exp. So let's make an example. Suppose I want to know the semantics of this. Let's say let x equals 2 in plus xy. And, well, what are the free variables here? The free variables are plus and y. So rho of plus is the addition function. It's the addition function. And let's say rho of y is 3. And rho of x is undefined, or it doesn't really matter what rho of x is. So then what should this be? This should be the value of this expression over here, the expression after the in. It should be the value of plus xy, but not in the same environment rho, but in an environment where in addition x is 2. So it should not be just rho, but x should be 2. So it should be rho, but in addition, we know what the new meaning of x is, namely the meaning of x is 2. And remember that we use this plus symbol to extend environments. And now when we are here, we have extended the previous environment rho by an additional declaration, and this additional declaration tells us that now x has been defined to be 2. And we do it in this order because in case rho said something about x, for example, x was 5 in rho, then that doesn't really matter because this global declaration of x is overwritten by this local declaration. So x is 2. And we are only interested in rho for all other variables except x. And then, well, this can be evaluated because we know what plus means. Plus means addition. X means 2. Y means 3. So this is the addition of 2 plus 3. So the result will be 5. So whenever we have a let expression, we have to extend the environment. So let's try to define this formally. So how should we do this if we want to know what is the value of this? Let var equals x in x prime in some environment rho. So we should take the value of x prime but not in the original environment. I mean, for most variables we take the original environment, but not for var. For var, we have a new declaration, namely this one. So we have to extend the environment, and for var, we now have a new value. So what is the value of var? Well, it's the semantics of exp. So it's the semantics of exp in the environment rho. So this means that as soon as we have this variable, then its semantics should be the semantics of this. And for all other variables, we look at the environment rho. And then the whole let expression has the semantics of x prime as its value. So that makes sense, except that it doesn't work for recursive definitions. So now let's regard the more problematic case. So now we regard also recursive declarations. So also regard recursive declarations. Okay, so let's make, this was a non-recursive declaration because x is on the left-hand side, but x does not occur on the right-hand side here. We had just the number 2. So we knew the semantics of 2 before, and then we can assign the semantics to x in the new environment. If we have recursive definitions, then this is not so easy anymore. So let's look at an example. And our standard example for recursive declarations was the factorial function. So let's define the factorial function. We have to do this in simple Haskell, so it will look like this. Let fact be the function which takes an argument x, and if x is negative, smaller or equal to 0, then we return 1, and else we return the factorial of x minus 1 times x. So let this declaration be used in the expression fact2. And the question is, what is the semantics of this thing? So what is the semantics of this expression in some environment rho? And of course, we want to do it essentially in the same way as we did it before. So it should be the semantics of fact2. But in some new environment rho prime. And this new environment rho prime should be like rho, except for the variable fact. For fact, we have to take this new declaration into account. So this is like rho except for fact. Now, why can't we use the definition that we use for non-recursive declarations? Well, because if we do that, in rho is probably undefined for fact, because we haven't defined the factorial function before. Then what we did here was we said, well, let's extend the current environment such that this variable now gets the meaning of this expression in the environment. The meaning of this expression in the environment rho. This is what I wrote here. So the variable gets the meaning of expression in the environment rho. But now, since we have recursion, we are defining a new variable fact, and this occurs on its own right-hand side. And therefore, in this environment, fact is not yet defined. And so we cannot say that the meaning of fact should be the meaning of this right-hand side, because in the right-hand side we have, again, fact, and we don't know the meaning of fact yet. We just want to define the meaning of fact. So that's a problem, but we discussed about this problem before already, and you may remember that we introduced this idea of least fixed points. And this is exactly where we need it for. So if we write a recursive definition like this, then the meaning is fact should be the function which is the least fixed point, or the smallest function satisfying this equation. So except for fact, the variable fact should be mapped to the, well, smallest, in the sense of as undefined as possible, to the smallest function that satisfies this defining equation. The defining equation fact equals lambda x goes to ... And smallest means as undefined as possible. And this, of course, we can also express in terms of least fixed points. So in other words, fact should be the smallest fixed point, the least fixed point of the function that maps the variable fact to the semantics of the right-hand side of this declaration. So the semantics of the variable fact should be the least fixed point of the following function ff. Of the following function ff. And what does this function do? Well, this function maps the left-hand side of this defining equation to the right-hand side. Or in other words, it's the function which computes better and better approximations to the factorial function. So maybe I first write some intuition about ff. So ff maps every function d to the meaning, to the semantics of the right-hand side of the defining equation of fact, to the right-hand side of the fact declaration, where in this right-hand side the occurrence of fact has the meaning d, where fact is interpreted as the function d. So let me write this down and then we illustrate it. So ff is a function from DOM to DOM. And it looks like this. So it takes some element of DOM, and this is one approximation to the factorial function. And ff computes the next better approximation to the factorial function. And how do we do this? Well, we take the right-hand side of the declaration of fact, so this expression, this lambda expression here. But we use an environment where fact is interpreted as the function d. So it's the meaning of the right-hand side of the factorial declaration. So lambda x, if x is smaller or equal to 0 than 1, else fact x minus 1 times x. And in which environment? Well, for most variables it's like rho, but not for fact. Fact is interpreted by d. So let's see what this ff does. So what is ff applied to bottom? Now, what is this? What is ff applied to bottom? Ff applied to bottom will be, if you look at this, it will be a function. It will be a function that takes some number. It checks whether the number is negative. In this case, it returns 1. And otherwise, it returns fact x minus 1 times x. Now, what does fact mean? Fact means d, so fact means bottom. And, well, minus and times, they mean what you expect. But since fact will be the bottom function, this will be a function that is defined only for negative numbers. There will be 1, and otherwise it's undefined. So this is a function which returns 1 if x is smaller or equal to 0 and bottom otherwise. What happens if we apply ff twice? So ff applied to ff bottom. This will be also a function. But, well, if x is negative, then clearly it will be 1. If x is 0, then, if x is 1, then we will call fact of x minus 1. So if x is 1, then x minus 1 is 0. And so in this case, we call the approximation before, and we will find out it computes the right thing for x equaling 1, and otherwise it's bottom. And, well, if we apply ff 3 times to bottom, then we get the next better approximation, which does the right thing up to x equals 2. And the next approximation will be doing the right thing up to x equals 3, and so on. So, in other words, ff applied 0 times to bottom is the function fact 0 that we had earlier, and ff applied 1 time to bottom is the function fact 1, and so on. And we have seen that this is a chain of functions which goes closer and closer to the real factorial function, and the semantics then can be defined as the least upper bound of this chain. So the semantics of fact then is defined as the least upper bound of this chain, or let me write least upper bound like this. So it's the least upper bound of the chain fact 0, fact 1, and so on, which is the least upper bound of ff applied 0 times to bottom, ff applied 1 time to bottom, ff applied 2 times to bottom. And we know by the fixed point theorem this is the same as the least fixed point of ff. So by the fixed point theorem. So the semantics of factorial will be the smallest, will be the function as undefined as possible, which is a fixed point of this. So if we insert the right factorial function here, then we will get the right factorial function back as a result. So what we will do here is the following in our example. We wanted to know the value of this let expression. So let fact be lambda x dot blah 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 in fact 2 in some environment rho. So how can we define this now? Well, we've seen that the idea is to look at fact 2 and take its semantics. So we take the value of fact 2, but the question is in which environment? And the environment is, well, everything except fact. We look into the environment rho, but for fact we do something differently. Namely, for fact we take the least fixed point of this function ff. So it's rho, but not for fact. For fact we take the least fixed point of the function ff. So this will be the definition. And of course, now we can formulate this in the general case, because we can always build a function like ff. What does ff do? It simply maps any element of the domain to the right-hand side of the declaration. And the environment changes by interpreting this function that we just want to define by this element of the domain. So let's formulate this in the general case. OK, but I have to wipe the board. So how do we do it in general? Well, we want to define the semantics of such a let expression. Let var equals exp in x prime in some environment rho. So the semantics of this will be the semantics of x prime in some environment which results from rho, but we modify it for var. And now var should be interpreted as the least fixed point of some function f. And f is a function operating on the domain. So what does f do? F takes an arbitrary element from the domain, and you can think of this as an approximation to the definition of var. And it maps this approximation to the next better approximation. So the next better approximation can be obtained by taking the right-hand side of this definition, but all the occurrences of var in here are interpreted as d. So this approximation is mapped to the next better approximation. The next better approximation is exp, where everything is done as rho says, but if this variable occurs here in a recursive call, then we interpret it as d. So this variable is interpreted as d. And so now we have the definition for let expressions with recursion, and this is also on the slide here. And of course, the question is now we have two different definitions, one for let expression with recursion and one for let expression without recursion, and that's of course ugly. And the question is, do we still need the definition for let expressions without recursion? So this definition on top of this blackboard. And well, it will turn out we don't need this anymore. So this also works for non-recursive definitions. This also works for non-recursive declarations. Why? Well, what happens there? So there we would now also take this definition. So we would say the semantics of the whole let expression is the semantics of x prime in this environment here, rho modified such that this variable is the least fixed point of f. But now what is the least fixed point of f? So f of d is, again, the meaning of this right-hand side, exp in this new environment where this variable has the meaning d, but this variable doesn't occur in this expression now. So it doesn't really matter what this environment does on this variable. It's the same as the meaning of this expression in the environment row. Since now, if we don't have recursion, then this variable does not occur in the free expressions of x, in the free variables of exp. So what is the least fixed point of this function if d plays no role here? Well, fixed point means that an argument is mapped to itself. And no matter what d is, the result of f is always this. So this does not depend on d anymore. And therefore, the only fixed point of f is this. Only if we have this as the argument, we get the same thing back. So the only fixed point of f will be, not var, but val, of course, will be the value of this expression in the environment row. And so this means that this least fixed point here in the non-recursive case is the same as the value of this expression in the environment row. And this is the definition for the non-recursive case that we had up here. So this non-recursive case is really the special case of this general definition in the case where the variable does not occur free in this expression over here. So we can really use this definition both for recursive and non-recursive declarations. Okay, so this is probably the most complicated part of the definition of the semantics, but I mean, we have seen this idea of least fixed points before, and it's just the same idea that we illustrated some lectures earlier with the factorial function already. So now we have the semantics of almost all expressions. The only one that's missing is lambda, and the lambda expressions, and well, nothing surprising happens here. So the last kind of expression that we have to look at are lambda expressions. So what will be the value of an expression of this form? Lambda var goes to exp in some environment row. Well, the meaning of this should be a function. That's the idea of these lambda expressions. So it should be some function f in functions in DOM. And what should this f do? So what happens if I apply this f to some object from the domain? Well, what should it return? Essentially, it should return the meaning of this expression, because it should be a function that maps arguments to this result. So it should essentially return the value of this expression. But in which environment? Really in the environment row? Well, not quite, because this variable, of course, plays a role. This variable might occur over here. And so whenever this variable occurs over here, then we should interpret it as d. So it should be row, but whenever the variable occurs in the expression, then we should interpret it by d. So let's make an example. So what happens if I want to find out what is the value of lambda x goes to plus xy in an environment row? And let's say, I mean, row has to be defined on all three variables. So row has to be defined on plus and on y. So let's say row of plus is the addition function, and row of y should be 3. Then what is the meaning of this? It should be a function f, where if I apply f to some object d, the result should be the value of the expression over here, so of plus xy. But in a new environment which is like rho, but this variable here, this x, is replaced by d. And, well, what's that? Well, it's in the end, it's the application of the semantics of this. So it's rho of plus, which is the addition function, applied to rho of x, which is d, and rho of y, which is 3. So it's the function that takes an argument and increases it by 3. And that's exactly what you would expect if you know that the meaning of plus is addition and the meaning of y is 3. So we have now formally defined what this backslash means, this lambda, that this really means it's a function that maps the variable to the value of the expression. So this concludes the definition of the semantics of simple Haskell. And now we have indeed formally defined what all these simple Haskell constructs mean. And, well, the crucial points are, the most crucial point, of course, are recursive definitions. That a recursive definition really means it is the function that satisfies this equation, but it should be as undefined as possible. So whenever the defining equation does not require it, then the function should be undefined. And, well, moreover, we defined what if then else means and what lambda means and so on. And now the next step, of course, is to extend this to the rest of Haskell. And let me say something about that after I wipe the board. So we've defined the semantics of simple Haskell. Now what about the semantics of complex Haskell programs? So those which go beyond this subset that we have just regarded. So semantics of complex Haskell programs. And here the idea is we will not extend this val function further to complex Haskell, but instead we will present an automatic translation. So the automatic translation takes any complex Haskell program and transforms it to an equivalent simple Haskell program. So we will present an automatic transformation from complex Haskell programs to equivalent simple Haskell programs. And what is this transformation good for? Well, it's good for several purposes. So one purpose, of course, is the semantics. We will then simply say, well, whenever we have a complex program and the question is, what does it mean? What is its semantics? Then we say, well, the semantics of this complex program is defined to be the semantics of the corresponding simple program. So first transform it into the simple program, compute its semantics, and then you know the semantics also of the complex program. So the semantics of the complex program is defined to be the semantics of the corresponding simple program. It's defined to be the semantics of the corresponding simple program. So this is the one purpose of this transformation, and moreover, we will also use this transformation for the implementation, because after having defined the semantics of Haskell, we will then be concerned with implementing Haskell. So how would you implement a Haskell interpreter yourself? And it will turn out that if we have this transformation, we don't need an interpreter for full Haskell. we only need an interpreter for simple Haskell, because as soon as you have a complex program, you can first automatically compile it to a simple Haskell program and then execute the simple program. So this can be used for implementation and also for type checking Haskell. For implementation and automated type checking. So instead of executing or checking the complex program, so instead of executing or checking the complex program, we only execute or check the corresponding simple one. The complex program first transform it into a simple one, to a simple program, and then execute and check the simple program. And then execute or check the simple program. So in this way, we'll have a transformation which removes all the syntactic sugar and gives you back a simple program, and then we can work on the simple program. Now, how does that work? What's the main restriction in simple Haskell? The main restriction in simple Haskell is that we have no pattern matching. And so the question is, how can we get rid of pattern matching? So the main problem is how to get rid of pattern matching. How to transform a program with pattern matching into an equivalent program without pattern matching. How to get rid of pattern matching. And the solution is, we have some predefined functions anyway. So we have, the constructors, the data constructors are predefined. They are defined by the user. And there are also other predefined functions like addition and map and filter and so on. So we add a few more predefined functions. So the solution, add some more predefined functions, and then the complex program with the old functions will be transformed into a simple function, into a simple program, which uses probably a few more of these predefined functions, and they are needed to simulate pattern matching. So what functions do we need? Well, first of all, we need a function that is always undefined. So that's maybe not such an interesting function, but it's convenient to have this function. So we need a function which is just undefined, bot. So this you could define like this. And of course, this is simple Haskell, so we could also define it ourselves in simple Haskell, but it will be convenient to have this function. But we need some more predefined functions to get rid of pattern matching. And the next function, what does pattern matching do? Essentially, pattern matching is done to find out whether some actual argument is built with a certain constructor. So if you think of lists, for example, you can find out whether a list is the empty list or whether it is built with a constructor for the non-empty lists. This is something you can do with pattern matching, and if we want simple Haskell, then we cannot do it anymore. And so we add another predefined function which does this for us. So what we do is, for every constructor, constru, we add a predefined function. We add a predefined function which we call is a constru. And this predefined function takes one argument and says true or false. It says true if the argument is built with this constructor, and otherwise it says false. Which checks whether the argument is built with this constructor, with constr. So for every data constructor, we add such a function to the predefined functions. So for example, if we think of lists where we have a data constructor cons, we would add something like this. There would be a function called isAcons, which takes a list and it gives you back a Boolean. And now it finds out, is this list built with cons or is it built with nil? So if it is built with cons, it returns true, and if it is built with nil, then it returns false. And of course, if you have pattern matching, then you can define this function yourself. But in simple Haskell, you cannot define this function easily. So therefore, we add, for every data constructor like cons, we add this function. And now in simple Haskell, you can use this function and can use it to find out, is your argument built with cons or is it built with nil? And the other thing that pattern matching is good for is it extracts the arguments of a data constructor. So for example, if you know that your argument is built with cons, then it gives you the possibility to access the first element of cons or the second element of cons. So for every constructor, for every data constructor, we also need another function, argof, which gives me the arguments of this constructor. We also add a function argof constr, which returns the arguments of this constructor. And if we have such a function argof and such a function isa for every data constructor, then indeed it will be possible to convert every complex Haskell program to a corresponding simple Haskell program. Just to give you an idea how this looks like, suppose that we start with a complex program like this. So this is the append program, which you have hopefully seen before. And you can see this append program works on lists. It takes two lists and concatenates them. And of course, it uses pattern matching. And we will see in the next lecture how to transform such a program into a simple Haskell program. And the simple Haskell program will look a little bit more complicated than that, but not too much. So this will be automatically converted into a program which looks like this. And this does the same thing. And you can see how it works. It takes two arguments, the first list and the second list. And now instead of pattern matching, it uses these predefined functions isa and argof. So it checks whether the first argument is nil. And if not, it checks whether the first argument is built with cons. And if it's built with cons, it uses this argof to extract the arguments of cons. How this works in detail, we will see in the next lecture. But this gives you a little flavor of it. And the main message is you can convert every complex Haskell program into a simple one. Now, the next lecture is next Monday. So on Friday, there's exercise course. And on Monday, the next lecture will take place. But the next lecture, which will really present this automatic transformation, is only needed for the bachelor students. So the master students should take home the message, it works. You can do this automatically. And if you want to know how, well, you don't need to know how. So it can be done. If you want to know how, you can also come on Monday or look into the course notes. But the Monday lecture is only needed for bachelor students. And the next Friday lecture is again needed for everybody. OK, and the questionnaires you can either return today, or you can return them on Friday, or you can return them on Monday, whenever you want. OK, so see you next week.